So now we will start with our with the second version of our control, or the second design method of our control, digital control design, and this method is based on that we actually start from a discrete model. Okay, we start from a discrete model of our system, or our main system that we want to control, and of our sensors. So we try to obtain a discrete model of these. That's the first step, and then we design our digital controller in the Z domain right away. So in this method, actually, in this strategy, we are not designing the controller in the S domain as we did in the previous method, but we design our controller in the Z domain right away, starting from discrete models of our plant and our sensor. And then after we design, we can then go to the third step and just implement our discrete controller. Okay, so just one point to mention here is that regarding those two transfer functions, okay, we can obtain them either by something like bilinear transformation. So maybe we have the S domain transfer function of our system, and we want to obtain the G of Z, and we have the H of S, and we want to obtain H of Z. Okay, so let's say that that our system is described by linear differential equations. We have our transfer function in the S plane, and we want to obtain the transfer function in the Z plane. So we can use here, for example, bilinear transform, okay, that we explained in the previous lecture, to just go from the S to the Z. Another way is that we can actually try to extract those using system identification. And with system identification, basically you can obtain the Z domain transfer function in one step, because in system identification, let's say you apply some step input and you measure the response, both the step input and the measure. So this is usually, this step is usually done on the computer. So you easily can have, like, this can be discrete or digital samples on a computer, and you can also collect some digital samples from the response. So if you have digital samples, the input, digital sample, and the output, which means that if you want to obtain this, you can already obtain the transfer function in the Z domain right away using system identification. So what I want to say here is that if you have G of S, then you can obtain G of Z from a bilinear transformation. If you don't have G of S and you use system identification, you can obtain the discrete time transfer function right away, because anyway we use computers, so computers based on digital samples, so you can do that. Okay, so just to mention the main focus here in this lecture. So we discussed in a previous lecture about the aspects, or important aspects that we consider in the controller design. So here we are doing, as I said, everything is now in the Z domain. So here we have our controller, okay, GC of Z, and then we have our G of Z, which is this discrete transfer function, and we have also H of Z, okay, and Y of Z here. So everything is actually in the Z domain now. So we can design our controller in the Z domain right away. Note that once we have a transfer function like this, we can easily obtain the closed loop transfer function Y over R, which is GC times G divided by GC 1 plus GC G times H. Okay, so it's just basically the same rules that we used in the S domain transfer functions. Okay, so we mentioned that we had like three important aspects which are related to control design. So we mentioned that the controller architecture is one of them. Okay, so architecture is an important thing. So, for example, in the continuous time, we talked about PID, we talked about lead and lag compensators, or lead lag compensators, and things like that. So, but now since we are talking about digital control, so we have a digital PID controller, okay, we have digital lead and lag compensators, and so on. So this is the architecture thing, and the second point is we talked about the aspect related to the implementation, which is quite important actually when we talk about digital control. So this is also one other important aspect of control design, and then there is the actual design itself. So how you choose the parameters of the controller. So those are three important aspects related to the controller. In this lecture, we will try to focus on the first two, and in the second lecture, we will go into this one, because the design is a little more involved. It's not so different from the continuous time, but we just need to redefine some of our basics related to root locus and frequency response and things like that in the discrete time domain. But regarding the architecture, we will go through one of the most famous digital controller architectures, which is the digital PID controller, and also we will look into some of the important implementation related aspects which are related to digital PID. So we look into the structure of the PID, how does the digital PID controller look like from a structural point of view, and also how can it be implemented, whether in software or in hardware. So this is the next topic. So